Hello, welcome back to physics. We have our very next problem in motion with constant acceleration. The problem goes like this. A car has a maximum deceleration of 6.0 meters per second squared, and the driver has a reaction time of 0.5 seconds, 0.50 seconds. He drives at 20 meters per second, and he sees an obstacle 50 meters directly ahead of him. Can he avoid a collision? So this is a classic physics problem. And what you're going to find out in most of these problems is that once you do one of them, you'll kind of put it in your tool bag and you'll understand how to tackle it for the next time. I think this actually could be one of the first problems that a lot of people see where it's not going to be exactly clear what to do just from reading the problem. You really need to draw a picture, you need to see what's going on, write your equations down, and then they'll formulate a strategy. So again, let's read it one more time and then we're going to write the equations on the board. A car has a max deceleration of 6 meters per second squared. The driver has a reaction time of 0.5 seconds, whatever that means. We'll talk about it in a minute. He drives at 20 meters per second. He sees an obstacle 50 meters ahead. Can he avoid a collision? So ultimately you're trying to figure out, with the motion, with the variables in play, will the car come to rest, to stop, before the position of that obstacle? Because if you hit the obstacle, you're at the position of wherever the obstacle is. So we have to draw a picture of where the car is, where the obstacle is, what the motion that's happening in between them is, and then calculate where the car is going to stop. And if the car stops before the obstacle, then he can avoid a collision. If the car ends up going past the obstacle, then he's obviously hit the obstacle. So first thing I'm going to do is write these equations down again, because we're going to need them over and over again. So x is equal to x naught plus v naught t plus 1/2 a t squared. That's the first equation of motion. Next equation, v is equal to v naught plus at. Third equation of motion, v squared is v naught squared plus 2a, and then you have x minus x naught, which is your displacement, how far you traveled. So I think I'll probably just leave these on the board forever, just to kind of like leave them there. But what I want to do underneath this is I want to draw a little picture, and then we're going to formulate a strategy. All right, we're going to formulate a strategy. So the first thing we're going to do is we're going to say that we have a car, and my cars are blocks, just like always. So I'm going to help you out here and tell you this is a car, all right? And so it has some velocity. It's going at 20 meters per second. That's the velocity. And notice the units are already correct, so I don't have to convert any units. So it says a car has a max deceleration of 6.0 meters per second squared. It has a reaction time. We have to write that down. Let's go ahead and write it down right now. We'll just kind of write it down directly underneath it. We're going to say max acceleration is equal to negative 6.0 meters per second squared. So this is the first thing you need to do. You need to translate the words from the problem into the words of physics. See, in real life, we say decelerated. In physics, we never say decelerated. We say it accelerated negatively. That's what we say. That's how we keep track of if it's speeding up or slowing down. So the car is obviously going to be slowing down, so it's going to have a negative acceleration there. The positive x direction is this way, so we'll say this is, plus x direction or something. The negative x direction would be this way, so obviously the car's not speeding up. That would be a positive acceleration. It must be slowing down, which means it has a negative acceleration. We also say that we have some reaction time. And we're going to have to talk about what that means. You need to think about that. But it means 0.50 seconds. All right, now obviously the car is cruising down the road, having a great time. And then suddenly, we have some obstacle. And just like everything in physics, it's always a square of some kind. And just to help you out, I'm going to tell you, this is an obstacle. It could be a cow, could be a tree, could be a horse, I don't know, something. It's a box, right? Now, we have to do a little bit of translation. The problem says max deceleration, 6 meters per second squared, we got that. Reaction time, we got that. 20 meters per second, that's how fast he's driving. We wrote that down. And he sees an obstacle 50 meters ahead. We have to put that in our picture. So the distance between this and this is what? It's going to be 50 meters. So we're going to put something like this, 50 meters. From the front bumper of the car, you can call it, to the very front of the cow or whatever it is 50 meters. Now, the better way to write it in physics, I mean, this is true that this is the distance. But what really you want to say is that at x sub 0, the initial position of the car whenever we start this problem is 0 meters. And it's slowing down, obviously, all right? But the final position of wherever the I guess you don't want the car to be or whatever, you would say that that's 50 meters. So ultimately what we're going to do is we're going to end up calculating where the car comes to rest. And if it comes to rest at less than x is equal to 50 meters from its starting position, then we're going to say that he avoided the obstacle. But if we calculate the motion of the car and it ends up being 52 meters, the position of the car x is equal to like 52 meters down the road, then we're going to say that he actually collided with the cow and it obviously didn't avoid a collision. So we're going to define it this way. The initial position, this is the final position. We're trying to figure out if it's on one side or another. We have the acceleration, we have the time. Now we need to talk a little bit, I know that you know what the acceleration means, we need to talk about what this reaction time means, 0.50 seconds. I had to think about this a little bit too when I solved the problem. What it means is that you're driving down the road and you see something, but it takes time for your brain to realize that you need to do anything. So when you see any problem in physics that talks about reaction time, it means that it's something happened, but you didn't take any action at all for half a second. That's what it means. In other words, I didn't push on the brake for a full half a second. And then once I push on the brake, then I start decelerating. So what they want you to realize in the problem, but they're not really telling you in the problem, is that the acceleration or the deceleration, it doesn't really start until about half a second after the person sees the obstacle. And that's really important for you to realize because it's not stated. The problem could have said a car has a deceleration and he sees something, but he waits half a second and then he presses the brake pedal. Yeah, that'd be easy. Then you'd say, well, he waited and then he pressed the brake. That makes sense. But when you see reaction time, you have to think about it and understand what it means. So practically what it means is that at time 0, at position 0, the problem starts. The car moves along some distance before he even presses the brake pedal. How far does he move? We'll calculate it in a second, but we know the car is traveling 20 meters per second, so every second that goes on, the car is going 20 more meters down the road. But after this reaction time is elapsed, then the acceleration starts to occur. So there's almost like two problems going on here. There's what's happening before he presses the brake pedal, before the acceleration starts, and then there's what's going on after the acceleration starts. There's really two parts of the problem, and they don't tell you that. They don't say, hey, there's two parts to this. You might want to think about what happens before and after. That's the part of physics that gets tricky because they don't tell you these things, but you can figure it out by working problems and by getting practice. So what we want to do first, before we do anything else, is we want to calculate how far does the car go down the road during this time period when there's no acceleration happening during his reaction time period. Because then he's going to be even closer to the cow or whatever in this particular problem. So that's what we want to calculate first. Let me see, where do I want to do it? Yeah, let's do it right under here. Okay, the car travels at 20 meters per second during this reaction time period. And we want to figure out where does the car end up. So what equation of motion can we figure out from this? There's a lot of different choices, but we're going to look at the first equation. We want to know how far it goes down the road. We know its initial position. We know its initial velocity, it's 20. And we're basically saying how long of a time period we're looking at, half a second. And we know the acceleration, which is not, during the initial part, is 0 before he presses the brake pedal. So let's go ahead and use that equation. It's going to be x is equal to x naught plus v naught t plus 1/2 a t squared. Remember, this is the part of the motion, the part of the problem that happens before he even presses the brake pedal, right? What is his final position? That's what we want to know at the end of this reaction time period. His initial position, we're going to say at 0. Notice we started off our little graph. We said the initial position we're talking about being at 0. What is the initial velocity? Well, the car is going at 20 meters per second. And how long is it? Is he traveling at 20 meters per second? Half a second, right? Plus 1/2. What is the acceleration during that initial period? It's not -6. I'm talking about the period during the reaction time where he's like, ah, and he doesn't even like press on anything. The acceleration during that time is 0 because he's not speeding up or slowing down. And the time period, again, 0.50 squared, doesn't matter because you're multiplying by 0. You can see the distance the car traveled is just the speed times the time. It's just like a uniform motion that we did before. So the car has traveled this times this, 10 meters. So 10 meters during the reaction time period. This is not the answer, but it significantly changes the problem because really the problem was originally framed telling you that you had 50 meters in order to not hit this cow. But now we know that there's a reaction time period. The car travels 10 whole meters before he even presses the brake pedal. So after 10 meters, that's really telling you how much distance is left before he hits that guy. So let's go redraw the problem, kind of like almost like a reformulation of the problem after the reaction time has happened. So the real situation is the following. We have x is equal to 0. That's where the car started. But now we're past that. We're down where he starts to press the brake pedal. We have a car that's some distance down the road. So I'll say car, right? And then we have the obstacle in exactly the same location as it was before. Obstacle. Right? That's the same old obstacle. But what we want to do is we're going to say, well, the initial position when everything started was 0. But now we're going to say that the car is now in a new position 10 meters down the road, right at the moment he starts pressing the brake pedal. And let's look back at our original drawing. Originally, we said the car was at 0. And the obstacle was 50 meters away, so we labeled that as x is equal to 50. So we'll label this x is equal to 50. So in other words, nothing has changed. The obstacle is still 50 meters away from the initial place the car was when the problem started, but it just so happens that after the reaction period is over, the car is not here anymore. The car is really here. So what you really have, just to boil it down, is you really have 40 meters remaining. And that's what they didn't tell you in the problem. They want you to calculate it, that you have 40 meters left remaining. So now what you have to do is almost like solve the problem kind of starting over. There's two ways to actually tackle this. And I'm going to solve it two ways for you. The first way I'm going to solve it for you is a little bit of a, I don't want to say harder way, but takes a couple more steps. And then I'll do a second way, which will be a little less steps, but I think that it's actually really good for you to see both ways so that you can kind of see two different ways of thinking about it. So the first way is going to be the following. We know the car started at 0. We know that we don't want him to be at a position x is equal to 50. But we know that after half a second, his position is x is equal to 10. So you see, when I have x is equal to something, that's the position of the car. X is equal to 0, x is equal to 10. We don't want it to be x equal to 50. Let's figure out what position the car will be when it stops. Is it going to be x is equal to 40? If it's x is equal to 40, then we missed the obstacle. Is it going to be x is equal to 49.9? Okay, we still missed the obstacle, but we're closer. Is it going to be, the stopping point of the car, is it going to be 52.3? Well, then we hit the obstacle, and so on. So what we want to do is calculate the final resting position of the car in terms of x. So what we would usually do is we would jump into this equation, because this is the equation that usually we calculate the final position of the car. The only problem is we want to know this. We know the initial position of the car, we know the initial velocity, and we know the acceleration, but we don't know anything about the time. We don't know anything about the time there. So the very first thing we need to do is figure out how can we calculate the time needed to slow down. And we look at this equation. We say, well, we know the initial velocity. I'm sorry, this is the initial velocity. That's 20. When it stops, the car is going 0. So we already know this one and we know this one. We know the acceleration, so now we can find out how long it takes to decelerate from here to a stop. That's what we want to find out. How long does it take? Because then we'll take that time and we'll use it to stick in the first equation to figure out where the resting position of the car is. So first thing we want to do is find out and calculate the time. Time needed to slow down. This is not the time from here, it's the time starting here, how long does it take to come to a rest? The equation is going to be v is equal to v naught plus the acceleration times the time, right? We know we're going to be resting at rest, so that's going to be 0 meters per second. We know we're going at 20 meters per second to start. We know the acceleration is negative 6.0 meters per second squared, and we're going to find out how long it takes to go from 20 to 0 at this acceleration. So what you have is you move the 20 over here, you get negative 20 is equal to negative 6t. You divide both sides by negative 6, and you get time is equal to a positive, because negative times negative is positive, 3.33 seconds. So what this means in our diagram, you don't have to write this kind of thing, but you can basically say that between here and here, it takes a time of 3.33 seconds to actually go from the point that it starts to hit the brake pedal, that's when the acceleration's happening, all the way to, I put the arrow here, I don't know exactly where the car stops. He might stop here, he might be stopping on the other side of the obstacle, I don't know yet. But I know that it takes 3 seconds, 3.33 seconds. And then I go and say, well, now I know how long it takes. Now I can calculate where the car is going to stop by using this equation, because now I know the time, and I know all the positions, and I know the accelerations. So now I'll figure out where the final resting position of the car is. So then we'll go and we'll do that next. And we will say, how far, or actually a better way to say it is, what is the final position of the car? That's what I'm basically trying to say. What is the final position of the car? X equals something. The equation what we're going to use is going to be x is equal to the initial position of the car plus v naught times t plus 1/2 at squared. It's the same thing. X here is going to be the final position of where the car is, so we leave it alone. What is the initial position of the car? See, now you're switching gears a little bit. In the previous equation, we just used it to calculate how long it would take to slow down. Now we're trying to put it all together, and this is going to be the final answer. What is the final position of the car? Well, this equation, remember what it means. This is why I spent time talking about what it means. The final position of the car is going to be wherever the car starts from, plus the initial velocity of the car times time. That's how far it goes due to its initial speed, plus how far it goes due to its accelerated motion. So the initial position of the car, to figure out where it stops, is going to be 10 meters. Yes, I know originally the car started at 0, but I guess what I'm trying to say is the accelerated motion happens here. And if you're just looking in this window, you want to find out where the car stops. This is x is 0. This is going to be x is equal to something way over here. There's an acceleration in this problem. So the window you're looking at when you apply that equation is during the accelerated region. But during that acceleration region, the car didn't start at x is equal to 0. It actually started at 10 meters away from 0. So this is one of the first examples where I kept telling you that the equation has initial position plus all these other terms. Most of the time, initial position 0. But in this case, I want to find out where the car stops. Its initial position from the braking period onward actually started 10 meters away from the origin. So the initial position of the car was 10 meters plus. What is the initial velocity? Well, it's 20. That's what we already said, 20. What is the time during this during this period of time? 3.33 seconds. Plus 1/2. What is the acceleration? The acceleration is -6. I'm just going to write it as -6.0. And then what is the time? It's again 3.33 squared. So you see, this is literally no variables over here. You've got everything in place. And so what you do is you say that x is going to be equal to, this is going to be 10, and then you multiply this, it's going to be 66.6. When you multiply all this out, you're going to get negative 33.27. I want to come back and talk about this a little bit in a second. And so when you add all these numbers together, you're going to get x is equal to 43.33 meters. So this is the final position of the car. But the position of the obstacle is at x is equal to 50 meters. So you can see we stopped well short of the obstacle. The car is somewhere here, so it avoided the obstacle. So we say, yes, they avoid obstacle. Okay, so that's all you have to say. You show that the car arrived at a final position, which is well short of the obstacle. So I'm going to go through it real quickly one last time, and then I want to draw some conclusions. Then we're going to solve it another way, which is actually even a little simpler than this. But what we do, first of all, is we say, well, there's a reaction time. The car from x is equal to 0 travels some distance during that reaction time. So we use this equation just during that time to say the velocity times the time means the car goes 10 meters down the road. So now the car goes 10 meters down the road. From this point, how long in seconds does it take to stop? So we use this equation and we calculate how long in seconds does it take to actually stop. So then we go back to the position equation and we say, I want to find out where the car stops. We know it's going to be its initial position plus some distance traveled due to its initial velocity plus some distance traveled due to its acceleration or involving its acceleration. Its initial position is no longer 0 anymore. The car during accelerated motion actually starts at 10 meters, so that's why we're adding to it, right, this guy. And we end up finding that the car stops short of the obstacle. Okay, we're done. A couple things I want to point out. Notice the way I broke this term out. I could have just wrote the answer, but I wanted to leave it 10 plus this, and you can learn a lot from this. What we're saying is that the final position of the car is equal to where it started from, plus some distance traveled due to the 20 meters a second that it started with, due to its initial velocity, right? Now, if the car were accelerating, actually with a positive acceleration, this would be a plus sign. See, the minus sign came from the acceleration. It would be a plus sign if the car was actually accelerating at 2 meters per second squared or whatever, or 6 meters per second squared, then this would be a plus. Then you would have its initial position plus how far it travels due to its initial velocity in that time, plus some additional distance traveled because it's picking up speed above and beyond its initial velocity. Then it would be a plus, and you would add them all together and get the final thing. But notice there's a minus sign here. So when you have a negative acceleration, what's happening is you have some initial position plus some distance that you would have traveled, I guess, if you had continued at that initial velocity, but you're subtracting off something here. You're subtracting it off because you're slowing down. Your speed started at 20 meters per second, but then it goes down. It's less than 20, maybe it's 18, then it's 16, then it's 15. So during that window of time, you're not going at 20 meters a second anymore, you're rapidly slowing down. This is the distance you would have traveled at 20 meters per second in that time, but it's going to be less than that because you actually aren't traveling at 20 meters per second the whole time. That's why it subtracts it off. So the three terms are very important for you to understand. Initial position, how far you would have traveled if your initial velocity were the same the whole time. And then you're either adding or subtracting something. If you're accelerating, you're going to add even more distance to that. But if you're decelerating, you're going to subtract something off because you're not traveling at 20 meters a second for the whole window of time because you're decelerating, right? Okay, one more thing I want to say before we close the problem out. This problem was centered around figuring out what was the final position and seeing if that final position was less than 50. But there's another way to think about the problem. There's always more than one way. What you can do is after you figure out your reaction time, 10 meters, what we know is that after the reaction time is over, the car is now 10 meters away from its initial starting point. So what we could do if we wanted to, and probably what I would typically do first, but I didn't here, is you can kind of almost like redefine the problem. See, the problem says, you know, deceleration, blah, blah, it's so far away, and so on and so on. You have a reaction time. But once you calculate that you've gone 10 meters, then the reaction time is done. That's totally finished in the problem. You don't need that anymore once you calculate how far you've gone. You can redefine the problem and you can say, well, okay, instead of the cow or whatever being 50 meters away from my starting point, I'm going to redefine it after my reaction time is over. In other words, it's easier to show with a drawing than it is to just talk about it. I can redefine the problem if I want, and I can say, all right, I have a new problem. It's different than the problem I had. I have a car, right? And I have an obstacle. I'm going to call it, let's just call it a cow. It's a cow. We don't want to hit a cow, right? And I can say that my velocity is 20 meters per second. And because the reaction time part of the problem is over, I can say that this is not 10 meters down the road. I'm going to redefine it. I'm going to say that this is 0 meter point. And now, if this is the 0 meter point, my original problem said that the cow was 50 meters away. But notice we even wrote it here. We said the cow's really 40 meters away after the reaction time. So I can redefine the problem and I can say, well, the cow's really at 40 meters away. So I can, in other words, then say that there's 40 meters distance between this car and this cow. And I can, of course, say that the acceleration is negative 6.0 meters per second squared. So in other words, the way I would rewrite the problem again, if there was no reaction time involved at all, is the following. A car has a maximum deceleration of negative 6 meters per second squared, and nothing about reaction time. So literally after that it says that he drives at 20 meters per second, he sees an obstacle 40 meters in front of him. Not 50, 40 meters in front of him. Can he avoid a collision? It's exactly the same problem. The only thing different is in the original problem we had a reaction time, which means we had a delay, which means now it's really only 40 meters away. So I can redefine it. Now I can say, well, I'm going 20 meters per second, this deceleration, 40 meters, can I avoid or not? And I look back at my equations. I don't have to do anything with reaction time. And I can actually find the answer even faster than the last time, because if I redefine the problem where x is equal to 0 and x is equal to 40, I can use this equation. So let me write that equation over there, and you'll see how it's actually a little easier to kind of deal with. v squared is v naught squared plus 2 times a times x minus x naught. That's the distance traveled. Again, in this problem redefined, there is nothing that happens before this position, before this 40-meter distance. It's not even part of the problem at all. The final velocity is 0. The initial velocity is 20 meters per second squared. The acceleration is -6 meters per second squared. And then you have x minus x naught. But x naught, we're saying is at 0. That's the starting point. We're redefining the problem. In the previous problem, we said it was at 10 meters because we're kind of taking the whole bird's eye view of the problem. But now we're redefining, and we're saying, forget about that stuff. I really only have 40 meters left, start at 0, end at 40. That's why I'm redefining and saying my initial position is at 40. What do I get? I'm going to get 0 is equal to 400 minus, this is going to be 12, and this is going to be x, because the 0 is basically gone at this point. So I have negative 400 is equal to negative 12x. So then the question is, what do I get? If I divide 400 divided by 12, I'm going to get x is going to be equal to 33.33 meters. And the question is, if this is my final stopping position, is it less than 40? And it is less than 40 because of what we said here. So it's less than 40, so yes, we avoid the obstacle. So we avoid it. We avoid the obstacle. So you see what's happened here. This is actually even a little bit easier to deal with because in the original problem, we kind of kept the bird's eye view of the starting position, and it was really like two phases of motion, one without any acceleration and one with acceleration. Then you need to break it up mentally. You find the time to slow down, and then we use the full enchilada equation to figure out where it ends up, including its initial position. You notice that in both cases, I figured out it took 33.3 meters to stop. Here I ended up adding that to 10, which gives me 43. So 10 was here, then you're comparing it to 43 over here, whereas here I calculate 33 and I'm comparing it to 40. So I hope I'm not confusing you by doing it two different ways. I'm just letting you know that there are more than one way, there is always more than one way to do a problem. It's very often convenient and easier to solve portion of the problem, get the answer, how far did I travel during the reaction time? Okay, now I'm going to redefine the problem. I only have 40 meters left, can I stop? But sometimes it might be easier or more convenient to take the whole thing, the whole entire motion from the 0 point and find the final position. There's two different ways to do it. Here I'm comparing to 40, here I'm comparing to 50, right? So make sure you can do that. It's not easy the first time you do these problems, but I promise you as you do more and more of them, they will get easier. Follow me on to the next lesson and we'll get some more practice with motion with constant acceleration.